This is Elizabeth Wilson, and today I'm really excited to share with you a talk that we're co-sponsored as one of the Andlinger Center Energy and the Environment at Princeton Distinguished Postdoctoral Fellow Seminars. This is brought to you as our new energy conversations with early career energy researchers with a host of other universities. And today this will be hosted by Jason Wren, who will be introducing Rebecca Ciez. So I'll sign off now, see you at the end, but just remember that you can submit your questions via chat and we'll go from there. Thank you, everybody. We're really looking forward to hearing what you have to say, Rebecca. And thanks again, Jason.
Hey, good morning, good afternoon, good evening, wherever you are. This is Jason Wren. I'm the acting director of the Andlinger Center for Energy and Environment at Princeton University. Thanks for Elizabeth for organizing this great, series. I love the title, New Energy, right? And today we are very glad to have Dr. I'm sorry, I was Rebecca to really talk about her research on designing energy storage for climate goals. And I would just give an introduction about Rebecca because she was one of our favorite postdoctoral fellows at Princeton. Now recently she moved to Columbia. So Rebecca Ciez earned her bachelor's degree in mechanical engineering from Columbia University and her PhD in engineering public policy from Carnegie Mellon. And she is currently a postdoctoral researcher at Columbia and was, until recently, a distinguished postdoc fellow at Princeton University, Andlinger Center for Energy and Environment. At Princeton, Rebecca was really a model distinguished postdoc fellow. She engaged in multiple interdisciplinary collaborations to really advance the center's mission of finding practical solutions for sustainable and public energy and environmental protection. Her work with faculty and researchers in engineering and public policy led to numerous publications and talks dealing with energy storage, systems, and transportation. We are also very pleased to actually congratulate Rebecca because starting this fall, she will join the faculty at Purdue University as assistant professor in mechanical engineering and earth and ecological engineering. So in there, she will focus on developing her research into new energy systems, including transportation, electricity, and industrial systems related to energy and environment. And with that, please join me in welcoming Rebecca to deliver her presentation, Designing Energy Storage for Climate Change, for Climate Goals.
Thanks, Jason, and thanks, Elizabeth, for both of you for organizing these different seminar series. I'm really happy to be here to present some of my recent research looking at batteries for decarbonizing and meeting climate challenges. And so when you think about energy and emissions, we know that transportation and electricity generation are the largest sources of greenhouse gas emissions in the United States. And obviously energy storage has potential roles to play in both of these spaces. So transportation has recently overtaken electric power as the largest source of emissions in the US, and obviously trying to transition to zero emissions vehicles, whether that's battery electric vehicles, or potentially fuel cells, is one way to mitigate that. But energy storage also has a role to play in electric power generation moving forward. And so the EV market, there's been a lot of development in that space. There are a number of more vehicle models available today in the US than there were back in 2011 when there were fewer than 5. Today there are almost 50 different vehicles you can choose from. And globally, the market share of EVs is trending upwards. Right now it's about 2.5%. There might be some shocks because of the coronavirus pandemic, but generally the trend long-term is still looking up. But what about the power space? And so we see that renewable electricity is becoming extremely cheap. And so this is a map circulated, it was created by the UT Austin Energy Institute, looking at what the cheapest source of electricity for new power plants is in each county in the United States. And so what you see a lot of is this blue regions, which means that wind or solar is the cheapest new form of electricity. There's some of this yellow color, which means that natural gas is still cheaper. And then finally, what you don't really see on this chart is coal. And so coal is being phased out more and more in the United States, and it's potentially being replaced by wind and solar, which is being bid at really, really low costs, right? So today, these new power projects in Texas, Alberta, Colorado, they're bidding to deliver renewable electricity at the cost of 2 to 3 cents per kilowatt hour. And so these are pretty different places. It's not just that there's a lot of solar in California anymore. These are pretty diverse markets that are being able to deliver very inexpensive renewable electricity. But obviously renewable electricity is not as consistent as a power plant that you can just turn on and off. And so we want to be able to store the electricity that's produced when wind and solar resources are available to meet demand at other times of the day when people want to be able to have electricity. And so when you think about the role that batteries can play in the grid, what we're using today is still largely borrowed from other applications. And so lithium-ion battery research really started in the 1970s. They were commercialized for consumer electronics in 1991 by Sony. And so basically every new application has been largely borrowing from what's existed. So in the 2000s, they were taking the lithium-ion batteries from laptops and putting them into electric vehicles. And what we've seen recently is that you're essentially doing the same thing, taking the lithium-ion batteries from electric vehicles and putting them onto the grid. And so this is a project that's under construction in California, where they're replacing a natural gas power plant with Tesla batteries. And so when you think about what you want to be able to do for real renewable integration in the grid, you're thinking of different challenges on different timescales. And so on the order of seconds, you're thinking about how do you provide resources for frequency regulation or reactive power control, be able to do black start or synchronous reserves, and then finally starting to get into these peak shaving or peaker replacement. And so what all of these applications have in common is that they're relatively high power. So you're not really providing energy for a long duration of time, but you need to be able to deliver electricity quickly. And so the batteries that we're pulling today from electric vehicles are already able to be competitive in this space, right? So you need your car to be able to accelerate quickly. And so there's already a sufficient power density in those batteries to meet these demands. And the markets for these different services have high enough prices that you can recover your investment on what is still a pretty high capital cost on lithium-ion batteries today. But longer term, what we're really looking at is these renewable integrations. So how are you shifting for hours of demand that are when you have overgeneration in the afternoon to the evenings and the early mornings when people actually want to use electricity? Could you potentially do island operation of microgrids, and then potentially even looking at some seasonal storage applications where you're really looking for having high energy density batteries? And so when you look at what's actually happening on the grid, you see that the electricity peaks are driven by both renewable output and human behavior. And so this is the California ISO's duck curve for those of you who might not be familiar with it. So basically this is net load accounting for what they were predicting what would be solar generation based as solar capacity increased from 2012 when they made this prediction to 2020. And so what we see is in the early mornings or late at night, nobody's awake, so nobody's really using all that much electricity. As everybody wakes up, you see this initial spike as people wake up to go to their office. In the mid-afternoon, net load drops because there is a lot of solar electricity being generated. But around 5 o'clock, the sun sets and everybody's going home, and so everybody's turning on all of their appliances at their houses at the same time that solar PV is no longer available. And so that's really what's driving these different behavioral spikes. And so we've also seen that in recent years, electricity prices are actually starting to follow this trend. And so it's one thing to see this in the net load, but it's another thing to actually have market prices follow the same trend. And that's an important signal if you want to have storage technologies that can be profitable. And so what's missing from this California ISO predicted chart is the curtailed solar electricity that's already being generated. So today, depending on the season, there's a lot of electricity generated at solar PV power plants that's not being sold into the market. There's just not enough demand for it, and so they're forced to curtail that. And so the idea would be able to use a battery to capture that electricity, and then fill in these higher price demand times when people are using a lot of electricity, but there's not a lot of renewable electricity available. And we're starting to actually see that in some calls for proposals. And so this was a recent call from some community choice aggregators looking at long duration storage, specifically calling for an 8-hour duration battery at a minimum. And so when you think about what you would actually want to measure in a storage project of this magnitude, it's really important that the cost metric captures the cost of and value that storage is bringing. And so what you'll see a lot of times is different entities will have a cost adder for adding a battery to a solar farm, for example. And so what they'll often do is amortize the cost of the battery across all of the energy delivered from that power plant, which is interesting from potentially an investor perspective, but it doesn't tell you much about how much energy is actually being stored in that battery, how long the storage duration of that battery is, right? So you can have a cost adder for a 2-hour battery and a 4-hour battery, and there's nothing inherent in the cost adder metric that they're releasing that's telling you any information about the battery. And so what we were looking at is using the levelized cost of storage. And so what that means is what it accounts for is the capital cost. So how much should you have to spend on the battery? And so that's a function of your material choices and costs, but also manufacturing costs as well. The extra electricity you have to buy because there are round trip efficiency losses as you charge and discharge the battery. And so that's also a function of just the electricity price. And then finally, any operation and maintenance expenses, which is a function of the battery type and how complex the storage system is. And then finally, all of that gets divided over the stored electricity delivered over the system lifetime, which is a function of both the battery useful life, but also just grid demand. And so you talk to a lot of battery people and they'll say, you know, I cycle this battery, you know, for 48-hour cycles for, you know, a whole year, and it worked and there was no degradation. And you're like, that's great. But people you wouldn't cycle a battery every 48 hours, right? It doesn't match with how people use electricity. And so making sure that you're actually delivering energy and modeling energy in a way that matches with consumer demand is really important. And so in this, and taking that into account, what we really want for a grid battery, we'd want it to be extremely inexpensive, minimizing balance of cell components that aren't actually storing any energy. You're somewhat concerned about efficiency, but if you've got these really long charging and discharging times, you're not necessarily stressing the battery all that much. And then if electricity prices are from these renewable sources at extremely low costs, that is not as important. And then you want to minimize any recurring costs you have over time. And so to model each of these different components, we have different submodels that we combine. So the first is a process-based cost model to look at battery manufacturing costs depending on your design decisions. We do a simple model of battery performance to see how the batteries behave over this charge and discharge cycles. And we make some assumptions about the system hardware and integration costs. And then we used a use case. And so this is drawn from an ARPA-E proposal or call for proposals looking specifically at long duration storage. And I'll talk a bit more about what goes into that later. And so I know that this is a diverse audience, so I'm going to talk a little bit about lithium-ion batteries. And so hopefully I will give you enough of an overview that you know what I'm talking about when I talk about the system components. So all lithium-ion batteries are named because lithium is the charge carrier, but the materials inside the battery can vary a little bit. So each battery has two electrodes, a positive and a negative electrode. So the negative electrode or the anode is typically made of graphitic carbon. So, and that's common across all almost all commercial lithium-ion batteries today. So things in your phone, your car, an EV, anything else, is you're looking at a graphitic carbon anode. Then you've got these the positive terminal or cathode, which is made up of a bunch of different types of materials. And then finally, there's an electrolyte, which is typically an organic liquid that's used to shuttle the lithium ions between the two. And so the energy density of the battery really depends on the voltage difference between the two electrodes. The specific capacity, most of the differential is driven by what's happening at the cathode. So cathode materials can vary widely. Some of them have really expensive transition metals. So there's a lot of discussion about how can you remove cobalt from certain formulations and increase the use of nickel or manganese that are less expensive. And so there's a lot of innovation to improve the specific capacity of cathode materials, and then eventually to remove the graphitic carbon and just have lithium metal anodes. So what we really wanted to look at is looking at existing technology. Is there a low-cost cathode material that we could utilize that might not necessarily be the best for an electric vehicle, but might make a lot of sense if you wanted to do stationary grid storage at a low cost? And so then you've got this basic geometry. There are a few different ways and form factors that you can make battery cells. So the two that have been most common in the EV and large format battery space are these pouch cells, which are just basically big rectangles made up of individual sheets, and then these jelly roll cylindrical cells. So Tesla has these in all of their cars. We also considered another type of battery, which is a bobbin cell, which is generally bigger than the batteries that they're using in current EVs. And I'll talk a little bit more about this here. So basically, if you were to open up these different types of batteries, these pouch cells are made of dozens of these relatively thin layers of these two materials with separators in between. And so what you can do within the pouch cell is, depending on how much power you want to be able to draw at any one time, you can increase the thickness of the electrode material within these layers. And so by doing that, you're essentially devoting more of the battery space to energy storage rather than current collectors and stuff that's not storing energy. The other option was what we looked at is a bobbin cell. And so these are how they make alkaline batteries. So if what you're putting in a remote, if you busted it open, it would be a similar architecture. I do not recommend doing that. But so basically you've got one really thick electrode of both positive and negative within this bobbin cell with one current collector pin in the middle. And so instead of having these thin layers, you've just got one big electrode of each type within the cell. And so again, you're reducing the balance of cell components to minimize the actual hardware you have installed. And so based on those two different geometries, we built a process-based cost model to factor in what's happening at the factory level. And so to do that, you take every step in the battery manufacturing process, and you kind of figure out how many pieces of equipment you need, what kind of labor requirements there are, and you can build a model depending on how many batteries you're trying to produce. And so, as you can imagine, you've got your first machine. As you increase the production volume, you see the cost per unit decrease up until a point, right? So you're using it to produce more parts, and so the higher utilization means each part costs less individually, but eventually you have to buy a second machine or you have to hire a second person. And so you see these spikes in the production cost that vary as you increase the production volume. But eventually you get to a point where it doesn't really matter that you've had to buy a second machine. You're still dividing by such a large number that you've reached an economy of scale. And so this is what I would consider economies of scale at a factory level. And so this helps drive decision-making if you're trying to make choices about what kind of batteries to manufacture, and provides insights into where there's opportunity to further improve costs. And so when you build all of these up, you can get one overall manufacturing cost per kilowatt hour, depending on the production volume of batteries. And so what we see is pretty consistent with what we've seen in previous studies looking at manufacturing EV batteries, that you're reaching these economies of scale at less than a gigawatt hour of annual production per year. Just for reference, I think Tesla's Gigafactory is currently producing about 30 gigawatt hours per year. They're looking to expand it up to 50. There are dozens, if not hundreds, of these scale manufacturing facilities in China. Europe's investing heavily. So these are definitely typical scales battery manufacturing capacity today. And so when we run this for each of the different types of cells that we were considering, we see that the pouch cell costs decrease as you increase the cathode thickness. And so basically what you're seeing is you're spending less per kilowatt hour on other stuff as the active volume increases. And so we see that there's pretty steep drop-offs, even especially if you go from like 100 up to 300 microns in terms of thickness. And then eventually you kind of reach this asymptotic value. And then the bobbin cell that we considered is somewhere in between. And so once we had these cells constructed, we wanted to simulate the battery performance. And so I'm not going to get into too much detail. We used an existing model out of UC Berkeley that lets you input specific parameters about the cathode material, and you get a first order approximation of the charging and discharging efficiencies, right? So basically the difference in what you would expect, the equilibrium voltage and the actual model voltage is what's driving a lot of this efficiency loss. And it varies depending on the battery, the type of battery you're producing. But overall, charging and discharging efficiencies are relatively high. And so then what was really important was to factor in a relatively realistic storage profile. And so as I mentioned, we were using some assumptions based on the ARPA-E long duration storage call for applications. And so basically what they're assuming is that you're providing about 8 hours of storage on a near daily basis, right? So if you were to think back to the chart with electricity prices in California, you're arbitraging from mid-afternoon when there's a lot of curtailment to provide enough storage for both morning and evening peaks. And then you've got these other longer duration storage events that happen with less and less frequency, right? So you can imagine that there might be a lot of days where days per year where there's cloud cover, and so you want to be able to provide 2 days worth of storage for those 2 peaks. And then as the duration of storage increases up to about 4 days, they're assuming that there are about 3 of those events per year. And so that bears out if you install additional storage capacity to meet that longer and longer duration, you see this linear increase in the kilowatt hours you have to install. But the annual electricity you actually deliver from that storage capacity drops off pretty quickly. So most of this is these very short cycles with relatively small additions from longer duration storage. And so when we account for that, again, with the cost of manufacturing, we see that you can achieve relatively low levelized cost of storage, and it's lowest when you're cycling most frequently, which makes sense, right? So if you're utilizing the capital you've installed more frequently, you can really drive down the cost of storage. And so we see that these costs of 5 cents or lower are generally pretty comparable for all of the different types of battery, the different configurations we looked at. So these pouch cells with different electrode thicknesses, and then the bobbin cell. And so we also ran some different sensitivity analysis, and we see that the levelized cost is relatively unchanged by changes to the operation and maintenance cost as a percentage of the installed capital cost. And then round trip efficiency also has a relatively minor impact on the cost of storage. And so lithium-ion batteries designed specifically for long duration storage can cost less than today's batteries. Reducing the balance of cell material relative to electrodes can reduce cell costs. There are existing low-cost cathode materials to help reduce the upfront capital costs. That does hurt on the back end. So some of my other research has looked at battery recycling. And if you want to recycle batteries, you have to have a lot of people are looking for high value materials to be present. And if that's not the case, it's less economical to do battery recycling. If you're looking at 4-hour applications, cell charging and discharging efficiency isn't terribly sensitive for these longer load shifting applications. And then you really want to have low O&M costs, which is helpful if you've got a closed form cell. And so I sort of mentioned seasonal storage, which definitely was not covered as part of this research. And so what are we talking about when we talk about seasonal storage? So basically there are these known patterns of reduced electricity output. If you've got wind plant capacity factors generally drop off in the summer, so they're called the summer doldrums. And then obviously during the winter, there's just less sun in the northern hemisphere. The opposite is true depending on where you're at geographically. But these are really predictable changes in electricity output. And if you wanted to do seasonal storage, just a quick back of the envelope calculation, assuming you're getting like 2 cycles per year, if you had these shoulder seasons, potentially, if you wanted to be able to deliver that at 5 cents per kilowatt hour, which is what the ARPA-E long duration target was, the capital costs would have to be less than $1 each, which is really, really infeasible when you compare, the asymptotic costs of lithium-ion batteries that we were seeing was around $60 per kilowatt hour. And so the way that I kind of think about this challenge is that less renewable energy isn't the same as zero, right? So if you know that there is going to be a change in output of solar PV in the summer or in the winter, that's easier to account for than these unpredictable, infrequent weather events that might, drop solar and wind generation to near zero levels. So if you have, this is an example from January 2019 in the MISO region. And so basically what happened is temperatures dropped to the point that wind turbines could not operate. Once you hit minus 30 degrees Fahrenheit, the gears freeze up. And so if they're frozen, you can't let them turn or else it'll damage the wind turbine. And so they had what's called a max generation event. And so everybody's cold, so you're using a lot more electricity than you might normally. They were expecting really high wind output, right? So there's a lot of wind in the Midwest in the winter. And so they had to do all of this work to import a bunch of electricity from different markets and different places where it wasn't quite as cold. And so how frequent are these real events? And can we diversify the electricity mix enough that we wouldn't have to worry about these events happening from a single source? And then are there mechanisms, other mechanisms to reduce electricity demand? And is there a value of using storage to essentially buy yourself time, right? So if you know, like if you have a 3-day battery and you're using the 3rd day's worth of storage, you were preceded by 2 days worth of storage, using 2 days worth of storage and kind of knowing that things weren't going great. And so is there other potential mechanisms that we could employ for these different infrequent events in a way that we haven't previously? And so just looking forward for the role for low carbon energy systems, today's grid storage projects have very, very short procurement times, right? So their projects are bid, installed, and then up and running within like 18 months in some cases. So it's an incredibly fast timeline compared to a lot of power plants. We see that lithium-ion batteries can provide lower cost storage, and there's still room for improvement. And so if you're looking at that as an incumbent, that's a pretty tough, looking at that as a potential new entrant technology, that's really tough to beat these existing markets, especially if you've got these really short project call times, right? So it's hard to enter that if it's your first big project. And then storage systems, or really anything that you would want to use infrequently, would have to be exceptionally cheap. And so if you wanted to do longer duration or seasonal or truly seasonal storage, we would have to be a very, very low capital cost, essentially zero. And so finding those solutions will be extremely difficult. And so with that, I'd like to acknowledge a lot of this work took place when I was at Princeton at the Andlinger Center. And then in true sign of the times, the most recent group photo is a Brady Bunch style Zoom photo. And with that, I will open it up for questions.
Great, thanks so much, Rebecca, and I will give you a big applause and great talk. So there are a few questions that were submitted. I'll just read them, and you can also look at them on Q&A session. And yeah, for everybody, if you have questions, please write via the Q&A icon at the bottom of your screen. So the first question, this is sort of this is by sort of the slides number. So the first question is about the cost. I remember there was a map, right? The US map relating to the sort of different costs, natural gas and the different regions. Yeah, that's the one. Is the cost reflected on the figure and the actual cost or cost after, including or not subsidies?
So I don't know enough about the methodology to know how different the subsidies are included. I would imagine that there's some variation across, depending on where you're at in the United States. But that is a good question. But a lot of these projects, you know, they're extremely low cost, even if there were subsidies, even if there weren't subsidies included, they're generally pretty competitive with natural gas.
Yeah, it will just be that even more competitive, like when we move along. The next question is on slide 7. And basically, Joe is asking why is the floor 22,000 megawatt is so high, and the high point is only about 1/3 higher. Is it the duck curve, right? I mean, basically, how would you see the difference?
So this is the duck curve, and right. So it's the state of California, so it's a pretty big state. There's a lot of people, so they're using a lot of electricity even at night, and so there's just a lot of variability on a daily basis, and so even if the baseline is pretty high.
Great, thanks. So next, 2 questions from Riza Moini, who actually just started to introduce. Riza is actually at Purdue right now, and he will be joining Princeton as assistant professor in the Civil Environmental Engineering department. He has 2 general questions. One is, do you see other sort of energy sources, marine or hydrokinetics, would have certain, I guess, potentials? And another one is, do you see other actually storage technologies that would be promising, you know, other than batteries?
So I don't know enough about the characteristics of marine technology. I know there's also a lot of talk about geothermal. Basically, if you've got a different variability that's different, that's generally an inherent good for you know, the electricity system. It's easier to balance if things are they don't have the same root cause, and so there's definitely benefits potentially from that. And then so I would say there's a lot of interest in having these other different storage materials, right? So we talk a lot about hydrogen, other materials, and it's just a really competitive market, right? So how do you compete against a battery that could be installed in 18 months and deliver relatively low costs? And so there's a lot of interesting stuff. There's even different battery storage. So like Form Energy has made a pretty big splash in that space, looking at, you know, a week's worth of energy storage in their battery. And so we'll probably end up having to have different solutions, but I think there'll probably have to be different support mechanisms to get those off the ground when you're facing these different incumbents. Yeah,
I agree, and certainly different process technology, as you alluded, like geothermal, other things, they have different, I guess, geographical application niche, and certainly the scale can be different, and hopefully they'll be complementary to each other as well. So the next question is about a slide 17. what are the factors affecting the efficiency curves? If you can explain that a little bit.
So basically what's happening at the bobbin cell is you've got a decent amount of overpotential. So basically you have such thick electrodes that there's like a traffic jam for all of the ions to make it all the way through. And so when you see that concentration difference, that's what's driving down some of the efficiency. You don't have the same challenge in a pouch cell with these thinner electrodes on these really, really long charging and discharging times compared to what you would test in like a car battery or a cell phone battery. And so that's why you're seeing these differences in efficiency.
Great. Slide 23. I don't know what that means. What is the northeast? Is that where we are? No, skating. 23rd.
20. So maybe it's 22. Yeah. So I cut off some of these for spatial reasons, so hopefully that everybody can see on their screen. But yeah, EIA makes these graphs for different places, and then yeah.
Okay, so next one is about cost. Regarding, say, return of investment, where do you see the sort of the revenue generation in terms, I guess, implementing the different battery technologies in this case, I guess?
Yeah, so really what you'd be looking for is to be able to sell electricity at these higher price times. And so if you're getting electricity at 2 cents per kilowatt hour, or potentially even zero. So what we've seen a lot is recently is existing solar PV plants are installing batteries in California to be able to make up for this price differential. So they're getting the electricity at zero because they can't sell it into the market. And then you're making up that difference in these evening and morning periods when prices are closer to 4 or 5 cents per kilowatt hour.
Yeah, for sure. Well, I'm just reading the question as we go, but the next few questions are actually quite related. If you can comment on some other, say, technologies compared to lithium ion, which you focus on, like sodium ion, or I think I've heard potassium ion, or even hydrogen storage, or even pressure conversion to energy. I mean, all these things. What's your thoughts on this?
Yeah, so there's a lot of interest in different, like so potassium or sodium ions. There's challenges with cycling those. Basically, lithium ions are popular and prolific because the lithium ion is like the tiniest charge carrier of these different salts. And so there are different challenges associated with those other batteries. And so they haven't been scaled up to the same degree. Hydrogen's interesting because you potentially produce it at relatively low cost. Basically, you've got big storage tanks of hydrogen. You've got an electrolyzer or a fuel cell that's using it or producing it. And so you've really fully decoupled power and energy costs in those kinds of systems. It's just a matter of whether the market's really demanding electricity produced from those systems, or if you're too far out ahead. And then what do you actually, can you store it in a way that's cheap enough? Can you compress the hydrogen in a way that's cheap enough? And do that at a scale necessary. So I think ultimately we'll probably have to explore these different options. But in the near term, it's really, really hard to get that kind of business off the ground just because you're competing against such a big incumbent of lithium-ion batteries.
Great. The next few questions is about actually our Jesse Jenkins, who is an assistant professor at the Ellinger Center, has a pretty, I guess, deep questions here. It's long. I'm not sure I should read it, or if you can you see the Q&A?
Yeah, let me pull it up. How long is it? Oh, wow.
Yeah, well, I can just read it. Because I'm not sure I can phrase it in a short time. So basically, he was looking at sort of the role of storage. I mean, including, let's say, I mean, battery can be just few hours, but for long duration options or form generation options like natural gas or other options, CCS, nuclear, biogas, hydrogen, ammonia. What do you think about the roles of all of the above, I guess, sort of different niches or competitors, or I mean, what do you see them in terms of their relationships, I guess?
So, I mean, if you look at like just looking out into like the near term, if you wanted to do deep decarbonization, you just have to build a lot of stuff. And so whether it's batteries, whether it's different, you know, technologies with CCS, that is just an astounding amount of capital that you have to install. If I do think that there's some competitiveness, I think for batteries to compete with like natural gas peaker plants, that we've already seen that. And then it's just a matter of like, what is the appetite to build some of these other technologies, right? So I considered if you were doing cycles of 8 hours per day to do this renewable integration, but I mean, could you potentially redesign batteries to do true baseload storage? And I don't know, maybe there is further opportunity there for batteries or different storage, energy storage materials, whether it's hydrogen and a fuel cell to do true baseload power in a way that we didn't necessarily model here. But I would imagine anything that you use a lot can be really cheap at the per unit cost and of electricity. And so I wouldn't necessarily rule out batteries. They're hard to model from a lot of from like an electricity dispatch model perspective. And so I see a lot of like the discussion of like, how do you get to 80%? People will assume that batteries only last for 4 hours, and that's not necessarily inherent to any battery or storage technology. And so I think there's opportunity to try and figure out like where the true limit of how long you would want a battery to be able to provide storage for. It doesn't necessarily, I haven't really seen a great answer to that. And that's something that I would want to see moving forward. And I would definitely look to people who do more like electricity grid modeling work to provide that kind of research.
That's a very tough question to answer, right? I mean, it's
yeah.
every process or technology has its pros and cons. That's actually what Professor Jenkins is doing with some other folks at the Ellinger Center to look at actually a pathway to achieve net zero, to achieve actually a rapid switch down to a greenhouse gas reduction. Sort of they look at the different options. So I think they're definitely a good opportunity to talk more. The next questions are sort of related to, sorry, my screen so keep jumping over. EVs, like the batteries that in the electrical vehicles, where they certainly present the opportunity using them as a certain storage, right, to link to grid. On the other side, how about the second life, right? After a few years, I mean, how is there a way we can reuse EV as a sort of fixed storage, energy storage option? And as you see, Tesla's being speculated like a lot, right? I mean, it's mainly like a battery company, I guess, a car company. So what your thought on that, linking the transportation, I guess, the fixed storage side of it?
Yeah, so there's been a lot of interesting work looking at, so I think there's two kind of interesting things around using EV store as a storage resource. There's potential services that EVs could provide to the grid if they're able to take electricity that would otherwise be curtailed. Even today, like today's technology, there's potentially flexibility you could introduce just from using the electric vehicle batteries as they are in ways that are most opportunistic. And so it's interesting from that. In terms of second life, I think moving forward as we get to these future lithium-ion battery chemistries and we've got more certainty about how they're cycling and aging, and we have better metrics for monitoring what's happening inside batteries in a non-destructive way, I think potentially could play a larger role. I don't necessarily see a lot of scaling of second life projects, and so it's been really hard for like the first generation of EV batteries to see, like if I drive a Tesla and you drive a Tesla, we've done different things, and so it's hard, you know, figuring out what's actually happening within those different batteries and cycling them at the same way, in the same second life application will probably lead to the best case scenario, rapid degradation of one of those battery packs, and potentially, you know, having charging them, potentially having safety issues associated with that. But as these battery packs get bigger and bigger and bigger, I think the batteries themselves have been holding up better over time. I think there's potentially interesting things from some sort of these second gen applications that we haven't really seen in the first couple of years.
There's certainly a lot of interest, like grid tie EVs or second use. There's a related question I think is very interesting as a sort of an environmental side of the center. What about like a I would say not expensive necessarily, like a non-renewable materials for battery? I mean, renewable materials for battery, not to use like those minerals, like say organic battery. I haven't seen that much. Do you see that like using some material that can be, I guess, biodegradable battery? I don't know, some other ways, like material-wise?
I think it has like there's like different like research cycles, and people have talked about these like biodegradable or organic batteries. There's definitely a much larger push to removing like the worst of the potentially toxic or hard to source materials, right? So there's a big push to remove cobalt from the batteries that are in EV battery packs. And so can you reduce those and have, you know, more nickel and manganese that are less resource intensive, but also produced in more ethical ways. And then, you know, can you bring online new sources of lithium that are potentially not as harmful, and just diversifying that kind of market space. But I would say there's still all these like alternative, like organic battery or biodegradable batteries are still pretty niche and research based.
Yeah, of course. And there are several, I guess, questions related to again, like you alluded earlier, like how do you sort of optimize the size of the storage system? That would sort of take advantage of the price variations around the, daytime, right, or night, and that, or even seasonally. Say, for example, if you build, my imagination, if you build a battery, you have a fixed storage capacity, right? But in summer, you may not use that much, or in winter, you may use more. How would, or depending where you are, how would you optimize that? That's why I think that in many ways, like your analysis will be actually very relevant, useful on those questions.
Right, so there's the costs of lithium-ion batteries, because everything is so coupled. You've got some ability if you can increase these electrode thicknesses, but we don't necessarily see very much differentiation in performance at these different timescales. But figuring out like where the true floor is from a market's perspective, and like where it would be so infrequently cycled that a 20-hour battery or a 24-hour battery just doesn't make sense. And that's the question that I don't necessarily have the answers to. I think that's probably more of a grid modeling question. But so from a lithium-ion battery perspective, you can essentially decouple them enough that you could meet those different performance requirements. On the hourly, on the daily kind of time scale. But beyond that, it's really, really hard to recover costs.
Well, the next question is much more beyond the daily or seasonal. So there's a question asking like, well, how do we build an infrastructure that will still be relevant and efficient 20 years from now, especially as lithium-ion plants are being built right now, I guess, big battery plants, like things like that. How do we make sure, I mean, we would build something that would still be sustainable, I think.
So like, how do you ensure that a battery you install today
yeah, will still be relevant.
yeah.
I think that's a sort of tied to Jesse's question. What about the afterlife of the batteries, and can we actually use them in a longer term? So that would extend ROI and things like environmental impact, reduction, things like that, I think.
Yeah, I mean, so I think the answers are sort of different for the EV side and the grid side. And I think a lot of people, so like even just looking at what's happened in the past, 5-10 years, a lot of battery capacity was installed in PJM to meet these high value markets. And it was installed to such a point that a lot of people lost a lot of money and are not making as much money as they thought they were going to, because there are just so many competitors in that specific market. I do think it's generally helpful if you're providing a lot of energy services to a lot of people. So just like law of large numbers, if you've got 0.1 times, thousands of megawatt hours a day of load you're serving, I think that's helpful. It is basically like, are you providing services to people who are relatively predictable? I know there's been some discussion of like whether like working from home will be more of a thing in the future. But it seems like in the aggregate, people use electricity and energy in ways that are largely predictable. It's a matter of whether you can overlay that with variations in these like meteorological sources of energy, and how you get those two to interact.
Two more quick questions. One is, what do you think in terms of, I guess, the value or cost, I would assume, between like vehicle to grid energy storage versus stationary batteries? We talked about that a little bit.
Yeah, so it depends what you mean by vehicle to grid. So they definitely can provide, the battery capacity is sufficient to be able to provide a lot of these high value, like short duration charging, discharging. Like a Tesla battery is like 100 kilowatt hours. And so depending on how much electricity your household is, how many people there are, that's like a couple days worth of electricity use in a lot of cases. And so there's a lot of storage capacity out there. It's a matter of whether EV manufacturers design and implement systems that allow you to actually perform those functions. And so there's a lot of concerns about warranting batteries, and they don't want to, plug it in and do something weird that they didn't design for, and then have it,
the warranty will
mess up your car.
Right? They don't want you, that makes sense. That there's certainly practical considerations. Last question is a little bit actually straightforward. Do lithium-ion batteries in a pack, they degrade uniformly, or would a few bad cells will ruin the whole pack?
So there are typically like some variation in how batteries age. They've generally been able to engineer around that. And so if you've got like one bad little tiny cell in a Tesla battery pack, like that will disconnect. And so the rest of the battery will kind of make up for it. And so there are ways to address that. And depending on how many of those cells go bad, it depends on like whether would ultimately affect whether you need to replace the battery pack or not.
Yeah, absolutely. Rebecca, I'll give you just 2 or 3 minutes to wrap up. Do you have like a final thoughts or anything you really want to sort of talk about, like in terms of the research and the questions we've talked so far?
Yeah, so I think looking at these longer duration applications is interesting. I do think that there's value to knowing that things in your system are not operating the way that you would want them to. And I think that's a potential area for trying to figure out like where the true limit of these this long duration storage should be. And so collaborating on trying to figure out where that floor is and where you can provide value to do like other demand response options by knowing that you've used several days worth of storage. And I think identifying that is important. And then again, just being able to design systems where you could potentially foster these newer technologies to compete with lithium-ion batteries, I think would be really important moving forward. So if we need all these different storage assets, we should be thinking of ways to create markets for them to be tested and deployed.
Absolutely, I can't agree more. Really, I think we'll just wrap up here. I'll give it back to Elizabeth. And thanks so much, Rebecca. That was awesome discussion.
Rebecca, that was just great. I study how decisions are made in regional transmission organizations. And so many times I was like, what if we're going to follow up on this, because I think about that market business case is so much how the grid rules and how the grid values all of these different services across these different timescales. And so I think we'll be able to have some really interesting conversations in the future. And I just want to thank you so much for participating in this series. And Jason, super job hosting. It was just great to have you here too, and have this co-hosted by the Andlinger Center. And so next talk will be coming up. I think Stephanie has the list of upcoming events. And the next one in this series is one that will be hosted by Paulina Jaramillo at Carnegie Mellon on the 29th of July with Michael Craig from University of Michigan, thinking about electric power and a changing climate. We have a few other events happening at the Irving Institute, Clean Energy in Caribbean Islands from Rocky Mountain Institute on the July 28th. And then August 12th, the next New Energy Conversations with Destine Knock at Carnegie Mellon University. So it's just fabulous to be able to hear from all of you in the research topics and how you're putting the information together. And I just wanted to tell you that you broke a new record today, Rebecca, in terms of attendance. So thank you very much. There were over 111 people who were part of this conversation. And this is a really important topic, and we're really happy you're working on it. And you are moving to Purdue to take on a job as an assistant professor in 1 month, right? So we know your students are looking forward to that too. So with that, everybody have a super Wednesday afternoon, evening, morning, wherever you are, and we'll see you all in a couple weeks. Thank you, everybody. Thanks, Jason. Thanks, Rebecca. Thanks for your time and efforts here too. And thank you to Stephanie, the Irving Institute, for making this all happen.